aloha mai kako. My name is Ian Kitajima. I am from Oceanet, and I will be your moderator for today. We have a great, incredible topic, which is the oceans and energy. And we have two world experts from the University of Hawaii with us today. I'd like to first introduce Richard Rocheleau, Dr. Rocheleau. Rick is the director for the Hawaii Natural Energy Institute. He has his PhD in chemical engineering for the University of Delaware and has decades of experience in renewable energy. So Rick is a world expert around renewable energy and has been doing this from the University of Hawaii's HNEI for decades now. So we will have Rick follow Professor Edward DeLong, who's a ocean explorer at heart, whose scientific interest focuses on science and technology development in microbial genomics, system biology, ecology, evolution. He's a fellow in the National Academy of Science in the United States, the American Academy of Arts and Science, and the American Association for the Advancement of Science. He's also the co-director of a center called CMOR. It's an acronym, and it's actually named after Daniel K. Inouye. It's the Daniel K. Inouye Center for Microbial Oceanography Research and Education, and for short, it's called CMOR. I'm totally fascinated. I'm totally excited to learn more also about CMOR. We're going to kick it off with Professor DeLong. Ed, I'm going to turn it over to you.
Okay.
So you can get us going, and I'm so excited to hear about microbiomes, the ocean, and how it actually impacts our life here on Earth.
Center, and our tagline, as you can see up there, is called Linking Genomes to Biomes. And what I thought I'd do in the short time I have is try and bring that to life for you, try and tell you why would we even want to study ocean microbes and why they're important and what we're looking ahead to in terms of understanding them. So our central mission really is to provide a comprehensive understanding of the microbes and their ecosystems in the ocean. And of course, here in Hawaii, we're strategically a place to do that. Now, I just wanted to start out with a couple slides on why would we care about these tiny things that we can't see. Well, most folks don't realize it, but actually microbes have been around almost since the birth of the Earth, if you will. So we think that the Earth's somewhere around 4.5 billion years old, and microbes got on the scene right about 3.8 billion years. So not long after the Earth's crust formed and the oceans formed, life was here. And in fact, very early on, microorganisms are sort of like little engines, little machines that can do amazing things. They can take sunlight and split water and bring CO2 out of the atmosphere to make new cells. And in fact, that was invented in microbes. And eventually, the microbes that invented that began to populate our atmospheres with oxygen. That gave rise to the evolution of larger organisms like plants and animals. So all the variety that we see around us today in the oceans as well as on land really had to do with the evolution of these little guys. Stephen Jay Gould, who's a famous evolutionist and geologist, wrote once that this is the age of bacteria. As it was in the beginning, is now and ever shall be. The reason he said that is because microbial life started so long ago, almost 4 billion years ago, and has been evolving ever since on this planet. As a consequence of that evolution, microbes live everywhere, in freezing seas and even on the ice in Antarctica, and as well as in hydrothermal vents, where waters are higher than the boiling point of water at 1 atmosphere, higher than 100 degrees Celsius, and microbes can still live there. Sort of amazing. And they live everywhere when you think about the ocean, throughout the ocean's water column. So they, at the surface, can basically incorporate CO2 using sunlight. They produce oxygen as a byproduct of that when they split water. So they give us both food and oxygen. These organisms are central to really supplying the food chain. And importantly, they can also draw CO2 into cellular material, where it sinks to the bottom of the ocean. So they're important regulators of greenhouse gases like CO2, and I'll say more about that later. I wanted to give you a sense because, we're talking about the future here and science and technology, the way we think about science and technology at Seymour. And if you haven't ever seen this book, since this is a book fair, I wanted to bring some books up. You certainly don't want to hear any music from me. But this book is fascinating. It's called Pasteur's Quadrant. And it's about how basic science and technology evolves in the different categories. And there's a notion in this book called Pasteur's Quadrant. It's really quite simple. You can imagine that there's two, extremes in terms of how we approach science and technology. One is pure basic research. And up here where you have a high level of fundamental understanding and pure basic research, we have as our hero Niels Bohr, who really helped us sort out atomic structure. And of course that's applied too, but when it was being really sorted out, it was very high detail theoretical physics. So that's pure basic research. And then you're down over here, this is Thomas Alva Edison. He was a businessman and inventor, and he really did some favors for us. We're going to hear more about energy later, but of course he was heavily involved in that. But as a businessman and an entrepreneur, he was really more interested in this area here, pure and applied research, both good things. But the way we think about this in Seymour is where you really like to be when you can, is in this use-based basic research sort of sweet spot here. And this is exemplified by Pasteur, because Louis Pasteur really helped solve problems of mankind in his day. And at the same time, he really pushed the basic science frontiers in terms of our understanding of the microbial world. So this Pasteur's Quadrant is where we like to get when we can, as we look at pure basic research and pure applied research at the same time. Our major goals in the context of understanding the microbes in the sea are to create and disseminate knowledge, innovate and implement new technologies, and improve models to inform society, help policymakers, and help protect the sea. Here's a final why do we care slide just to bring it on home. And it's interesting to contrast what we're used to on land versus what's happening in the oceans. So the forests of the sea are microbial. The forests of the sea are microbial. What does that mean? It means that unlike on land, where I'm looking out my window right now at these gorgeous trees, beautiful plumeria, many other beautiful plants that really help keep our terrestrial systems in balance and make half of the oxygen that we breathe each year. But the other half of the oxygen that's produced on the earth is produced by these little guys that you see here in these microscopic images. So these are little cyanobacteria called Prochlorococcus, and they're the most abundant plant on the planet. And they live right out here off of Hawaii and in all the open oceans. And what you see here are dinoflagellates and diatoms. These are just the different trees, if you will, that make up the forests of the sea. They're incredibly important because they feed the rest of the food chain. So the things that we like to eat need to eat these things and the things that eat them. And also they pull in CO2 out of the atmosphere and oftentimes sink and bring it down to the bottom of the ocean where it's sequestered for very long periods of time. So these organisms also help mediate the CO2 balance of our atmosphere. Well, as I said, Seymour is strategically placed. For the past 30 years, so our director of Seymour, David Carl, also started the Hawaii Ocean Time Series program. Here's an emblem for that here. And starting in 1988, over the past 30 years, every month, University of Hawaii has sent a ship out to Station Aloha, 100 miles north of Kahuku Point, 100 kilometers north of Kahuku Point, and sampled the ocean. I like to call it taking the pulse of the ocean. So we're giving the ocean a checkup every month, and we've been doing so for 30 years. And I'll tell you why that's so important in a moment here. Also, the reason why Station Aloha we're so lucky to have close proximity to an open ocean site is that one of the largest biomes on the planet is the North Pacific subtropical gyre, right where we all live here. So with these monthly checkups on the ocean for the past 30 years, we're really able to take the pulse and try and understand how our seas are doing. For the past 30 years, the Hawaii Ocean Time Series folks have been measuring the acidity of the ocean. What happens as CO2 increases in the atmosphere is that the ocean absorbs that, it becomes carbonic acid, and eventually forms bicarbonate and causes the ocean to become more acidic. So here at Hawaii, we should be very proud of this actually. We have the best record of atmospheric CO2 globally, and we also have the best record of what's happening to the oceans in terms of pH. And what we can see here, it's really going down. And of course, this has implications for all kinds of organisms, particularly those that use calcium carbonate for their skeletons or their tests. And of course, this is something that folks are really concerned about with respect to corals. So that's something we need to keep track of. And that's why these time series and taking the pulse of the ocean, looking at the environment around us and seeing what's going on is so critical. In fact, microbes are probably one of the single life forms that has the largest influence on climate processes in terms of natural life. That's not including us because we're pushing pretty hard on these systems too. And so we really need to understand this, the interaction between those natural processes and organisms that I just talked about and what we're doing to the planet with our growing population and burning of fossil fuels and so on. And this is an incredibly important area. It's one of the most critical and key areas mankind faces in terms of looking towards the future. So we hope that Seawater can contribute in a small way to understanding what's happening, where we are and where we might head, and maybe even help mitigate some of these processes. So that's all I wanted to say in this short time. Microbiomes matter in the sea, on land, and in us. And the ocean microbiome has contributed new knowledge to how the Earth system operates, what happens in these vast oceans, the North Pacific here, one of the largest biomes on the planet, and also has contributed greatly to sort of methods and techniques that have been borrowed and shared back and forth between folks that are studying, for instance, biomedicine or bioenergy, and what we do out here at Seawater. So thanks for listening, and I'd be really happy to take any questions if you have them. Thank you.
Okay, thank you, Ed. That was fascinating. Let me see. One question that came up is, what is the most pressing agenda for Seawater now?
That's a big question. And I think that probably it's the one I just stated. As I mentioned, you know, Seawater interacts very closely with the Hawaii Ocean Time Series, and they are continuing to track, take the pulse of the ocean, if you will. And I think that we're continuing to sort of get better and better about tracking these things in real time. So I didn't mention it, but things like remote sensing from satellites and autonomous sensing in situ are also very important components of these ocean observation systems. So I think one of the most pressing things really is to continue doing what we're doing. I'll have to tell you that a lot of times people think that time series are boring, you know, because you go out every month and you take the same measurements. And in fact, people probably don't know this story, but in the early days when Keeling started measuring CO2 at the observatory here in Hawaii, that almost got shut down because people in the early days thought that, yeah, measuring CO2 is kind of boring. Well, it turns out it's not boring. We really do need to continue to look around us, take the pulse of the planet. I mean, if you think about it, what happened with the ozone hole and how actually we mitigated our own efforts on that was super important. So sorry, it's a long-winded answer, but I think one of the most pressing things is to continue doing what we're doing would be my answer.
Okay, fantastic. I want you to also think, because I'm going to come back to you. Okay. I want you to think about if you can help us connect the work you're doing to the future and to students, and how we continue this, the importance of the time series. And that's going to require our young people in Hawaii to get more involved. So I want you to think about that.
Absolutely.
I want you to think about that, because I want to come back to you, because I want to come over to Rick Rocheleau. So Rick is the director for the Hawaii Natural Energy Institute. So I said oceans are important. Energy is very, very important. And Rick has been on the forefront of renewable energy here, not just in Hawaii, but around the world.
I think most people know we do not have any indigenous fuels in Hawaii. At least not of the non-renewable type. There's no coal, there's no oil, there's no gas. We're basically too new to have those resources. Each island is very unique, both in the generation mix that they currently use and the potential renewable resources that are available. And that's a plus and a negative. As a university person, when I'm trying to convince a funding agency to give us money, it's look what a great resource we are. We have 6 different islands. They're all different. We can test things in these different environments, and we can understand what to do. As a utility, it means you really have 6 different unique problems to solve with very different solutions and actually a very different set of issues when you get into it. And no matter how many times you say it, and people constantly ask, there are no interconnections between any of the islands. That includes between Molokai, Lanai, and Maui, as well as between the major islands. There were programs to look at that at one point, a number of times, one back in the 80s, others back in the early 2000s. But at this time, there are no movement in that direction, there are no plans. So every island really has to operate independently. And in spite of our really great progress in renewables to date, we are still predominantly oil-based. And that's looking at electricity. And when you look at transportation, even more so. We're right around that 30% number for renewables. So we are still about 70% fossil, with most of that being oil. With that in mind, we do have aggressive goals and policies, and that can be a discussion all of its own of how that's evolved over time. And if you look at the stage 1 projects, which have been approved by the Public Utilities Commission, they're going through some final approvals and permittings. They will actually take us from about the 30% we are at now up to 42% of our energy coming from renewables as an aggregate across the Hawaiian electric system. The utility recently put out a request for proposals. They got numerous bids. They down selected a number of projects. They are in front of the Public Utilities Commission for approval. I think that's the stage they're at. That will take us up another approximately 20% to the point where 62% of our electricity would be coming from renewables. And if you look at the 2 yellow bars, and if you add in the green, almost all of that renewables, certainly about 80% of it, is coming from sources that are variable, they're intermittent, and they're inverter based. They don't have generators with them. They don't have inertia. That is a very unique grid system, and it brings a great opportunity, great potential to reduce our dependence on oil, but a whole lot of technical issues associated with making those systems work right. In the seawater air conditioning realm, we're working with our Department of Oceanography. Basically, there's a private group trying to do seawater air conditioning in Honolulu. It's moving along. They have their permits. It's really a matter of getting customers lined up and getting the infrastructure going. But for future systems, we're trying to have baseline data, not too different than what's going on with some of EDGE monitoring, to understand the seawater conditions around those, particularly where the pipes will dispose of the slightly warmed water, so that information can be used in future systems to assist in permitting and assist in design. So very practical projects around the ocean, trying to move forward on a number of fronts and demonstrate how these technologies can eventually be useful in Hawaii.
Looking at that graph, where it's pretty amazing how by 2025, you potentially are forecasting something like 60% renewables, primarily because of the jump in the utility scale PV. How do we eventually, eventually the goal is 100%, and it seems like that's somewhat doable, but so how do we, how do we get there? Is it more utility scale PV? Is it distributed? Is it hydrogen? Like, is it cars? I don't know. What is that? What is your thought there? How do we get there?
Well, first thing, you have to separate kind of cars and hydrogen and storage. Those are ultimately, cars are load. So if we electrify cars, that's more electrical load, that's more electricity we need. So if I increase my load, percentages go down unless I generate more. Now, it's still a positive swap because I'm electrifying more. So you really have to look at the two together. And if you look at the utilities forecast going forward, the EV load is a significant part of their forecast. There is, the thing that's astounding about this graph is probably 3 or 4 years ago, people were really saying 20 to 30% was really doable. You really started to have reliability challenges. Very few people really visualize you could put wind and solar with this intermittency and variability and get to the 60 or 70% number. It really is battery technologies that's done that. We need to learn how to control them and really optimize their value. There's not a lot of experience doing that. They're probably, from a technical perspective, there is room for more solar. These systems do take up a substantial amount of room. They aren't necessarily going to be hidden from view. So, probably one of the bigger challenges in maybe even getting to the 60%, but certainly in the next increments beyond that, is going to be making sure the communities are well informed and they're engaged and that they're approving of what's happening and understand the value to the islands. It's really, the message really has to get out of what this means to the people.